In this lecture, I will derive the components of the gradient vector of a scalar function in cylindrical coordinates. My name is Carlos Thompson. What are the coordinates, the cylindrical coordinates? You see, here I have a cylinder, okay, and a plane, and another plane. This plane here is z is equal constant. This is the surface of cylinder. The radius rho, they're the same. This angle theta, and this is z. Okay, so a point P can be represented as rho, theta, and z. These are the cylindrical coordinates. Okay, this is the position vector R. The position vector obviously depends on these coordinates. Okay? Now, what I want to express gradient of a function, okay, a function represented, expressed in terms of the coordinate. This is a function, and these are the components of the gradient, which I don't know. See, I roll. Okay, as soon as I get a sub rho, a sub I theta, a sub z, then I conclude, okay, the gradient of this function. Now, what I will do, we know from here that the differential of f, partial difference, the differential of f is the partial of f respect to rho, the rho, plus see, this is from the mathematics, okay, that's very used. Now, on the other hand, we know that differential of this function f can be written as a dot product of the gradient of f dot dr. Now, let's express the differential of the position vector in terms of rho, theta, and z. Now, I will draw here I have this length, okay, and this is a volume, okay, here. This is the volume, okay. Now this length over here, okay, is rho the theta. You see, you can see here also. See? This length is rho a theta. Now, what the length of here, this length, okay, here, will be dz. Okay. Now, this over here is v rho. So, let's put colors on this. This is my length, v rho. This is my length, dz. And this is my length, rho d theta. So I can write dr is equal to rho d rho, okay? It's three lengths, okay? D rho plus rho d theta plus dz. Okay? That is the differential of the position vector. This is the position vector right over here. This is r, and this is dr. Okay? This is a sum of these three lengths. Now it's quite easy now. I substitute my gradient, the gradient, plus ez dot dr dot, this is now, since says a rho a theta a z, they are orthonormal basis. Orthonormal basis is they are orthogonal to each other, and also the magnitude of each of these unit vector, okay, is 1. Now I can do the dot product. E rho dot E rho is 1. So I will write right here, okay, this is equal. It's quite easy, okay? It's easy. I have a rho plus, now a theta dot a theta is 1, okay? A theta plus, now ez dot ez, az dz. Okay? Now, you can see here the df. Now I'm going to compare, okay? This is df. I'll repeat here, okay? df. It's the same df over here. You see? Here. Now I can compare, okay? A rho is partial of f with respect to rho. So I got a rho. This one, okay, is equal to partial derivative of f with respect to theta. So a theta is equal 1 over rho partial of f with respect to theta. If I multiply here, rho this a theta is equal to partial of f with respect to theta. And finally, AZ is equal partial of f with respect to z. So now I'm ready to write the gradient of the scalar function in cylindrical coordinates. It's very easy, very straightforward. Okay? And I'll write here. Del f is equal partial of f, the partial derivative of f with respect to rho plus partial f with respect to theta plus partial derivative of f with respect to z ez. Ez is the same as k, okay? This is what I wanted to obtain. It's quite straightforward, okay? It's very easy. Exactly is the procedure which I did for spherical coordinates, okay? It's very, very, very easy and straightforward.